I hope you have calculators. Huh? Yes or yes? Good. So it's a bad manners becoming a math class. So next one. Do you have a calculator? Hey. But you knew these numerical methods. You knew these numerical methods last. Today. Hey. Oh, so replace. So today we are going to introduce the course numerical methods. So we introduce the equation. Numerical methods. So the first page is a course outline. Outline. So the first chapter is what we call error analysis. So introduction to error analysis. Error analysis is the first chapter. The second chapter. Methods of solving. Methods of solving nonlinear equations. So this will involve the first one, bisection method. Bisection method. And then we have regular foci method. Regular foci method. Then we have Newton-Raphson. Method. Then we have what we call the second method. So these are majorly the method that we are going to dwell on this course. So after successfully going through this, then the other chapter is interpolation. Okay, before we go to interpolation, we can have finite differences. Finite differences. Finite differences. Then after finite differences, now we can go to interpolation based on finite differences. So interpolation. Based on finite differences. Interpolation based on finite differences. And then After this one, we will have Newton forward difference formula. The Newton forward difference formula. And then we have Newton backward difference formula. Then we have Bessel's interpolation formula or difference formula. We also have what we call Avery's interpolation formula, just interpolation. And then we have Newton-Gauss interpolation, and many, many more others. At least we have found another member of the group. And then so after that, there's what we call Lagrange. So this will be E. Lagrange interpolation. Then there's what we call Newton divided interpolation. Then we have what we call numerical differentiation. Here's the next chapter. Yes, numerical integration. So if you are able to finish this one, then it will be mature for the exam at the end of the semester. So the prerequisite for this course, which I would check before you are allowed to register. MAT120, this college algebra. Then MAT121, differential calculus. We have MAT221, integral calculus. And also MAT325 can also be found. Any algebra can also be. If you have already done this one, then this table take time. So that is the structure of the course program. It's a very friendly course. If you did it right from the start, and then you do a lot of practice. So this course will make a lot of sense, and you will be able to move to the next level without struggling if you do a lot of practice. Most of the things here are very friendly, but the problem which people faces is time, especially when you're doing the exam for this course. Many have failed not because they don't know, but because they don't know how to manage time. And also they don't know how to manage time because there's a lot of computations which are involved, which requires you to do practice so that the time given, say for the cut of the pen of the exam, should be enough to enable you under the required questions. So from today, as we start, ensure that you do a lot of practice. Don't wait for me to give an assignment before you start. Ask for assignment. Or if you don't ask for assignment, then share some books which will help you to actually get problems and solve them. So the trick is to do practice. There is no shortcut here. Whether you are from Alliance, you are from Startup, you are from Mango, practice is what is required here. And all the computations that are supposed to be done here need a calculator. So one of the key requirements also is a calculator. Calculator in this course is not optional, it's mandatory. So ensure that you have your calculator from day one. Welcome. You are looking for what is it? I'm doing another new course and a new register. So any question before we start? The grading system remains the same. A is from 91%. We have not changed, we are still there. So A is 91%. Fail is 40% to 0 to 40%. So pass starts at 21%. Ensure that you value your time well. As usual, I'll give a lot of assignments from today. As usual. Yeah. And the objective of the assignment is to enable you practice. So don't take them as a punishment. Take them as part of practice so that you don't get disadvantaged because of time. So so I'll share the detailed course outline where you can get the other nitty-gritties of the course and those chapters and the references. I'll also share some references to the class. Okay? So on a new page, before we start with the introduction to error analysis, as is the custom to any given course, let's define what we expect to study. So we say numerical analysis. Numerical analysis is a branch of mathematics. Numerical analysis is a branch of mathematics that provides tools and methods for solving mathematical problems in numerical form. Branch of mathematics that provides tools and methods for solving mathematical problems in numerical form. Okay. In numerical analysis, we are mainly interested in numerical analysis. We are mainly interested in the implementation. We are mainly interested in implementation and analysis of numerical algorithms, implementation and analysis of numerical algorithms for finding an approximate solution to a mathematical problem. For finding an approximate solution to a mathematical problem. I said, in numerical analysis, we are mainly interested in implementation and analysis of numerical algorithms. numerical algorithms for finding an approximate solution to a mathematical problem. For finding an approximate solution to a mathematical problem. Okay. Then let's define a numerical algorithm. Numerical algorithm. Is a complete set of procedures. Is a complete set of procedures which gives an approximate solution to a mathematical problem. Is a complete set of procedures which gives an approximate solution to a mathematical problem. So then, objective of the code, even before we start the error analysis, know that what we are going to do throughout this course is to objective is to minimize errors in applications. Remember what we are going to discuss, almost all the problems are going to discuss under solution of nonlinear equations is to approximate the roots of equations. And then the approximation process, always remember, the objective is to minimize errors in all the equations. So we try as much as possible to reduce the size of error. Good. So, introduction to error analysis. Introduction to error analysis. Introduction to error analysis. Okay, how many kinds of numbers do you know? How can we classify numbers? How many types of numbers do you know? You are the famous Ben Jason. Hey, my name is very difficult. So how many types of numbers do you know? I'll give examples then. Odd numbers, even numbers, real numbers, odd numbers. Any other? Rational numbers, irrational numbers, such, okay? Yeah, but then now in this course, we are going to actually classify them into two groups. So those depending on the course you're studying, like say you are studying discrete mathematics, then those are special numbers to discuss. But here we are going to split all the numbers into two big parts. There you say there are two kinds of numbers. So for this course, there are two kinds of numbers. There are two kinds of numbers. Then exact numbers and approximate numbers. So in this course, we view numbers just in two dimensions. So is either a number is exact or a number is approximate. Then you say an approximate number, x an approximate number x, or x, we actually put a bar x. So we'll be using this notation. If I put a bar, I mean it's an approximate number, okay? So this just is not, it's just the convention we are going to take. But if I put a bar, I mean an approximate number. So an approximate number by x is a number that differs, slightly from an exact number x. An approximate number by x is a number that differs slightly from an exact number x. Used in the place of the letter in calculations. Used in place of the letter in calculations. So letter there refers to the exact, okay? Yeah. E.g., the numbers 1.41 and 1.414. The numbers 1.41 and the number 1.414 are approximate values of the number √2. Are the approximate values of the number √2. Okay? So in this case, 1.41 can be used in place of √2 the calculations. Or you can use 1.414 in the place of √2 for calculation. Okay? Yeah. So √2 is the exact number. Next slide is saying the numbers 1, 2, 3, say 3/5, say 3/7, 5, E, etc. are all exact. The numbers 1, 2, 3, say 3/5, 3/7, 5. The number E, etc. are exact when written in this manner. Are exact when written in this number. Are exact when written in this number. But do you know that we have a celebration on March 14th? You know that? March 14th of every year we celebrate. That's the only holiday we have in March. So 3.14. So 14th of every March, every year we celebrate. Which celebration? Which celebration is in March? Huh? Rangers. We celebrate 5 on 14th March of every year. We celebrate this number 5. But then what's the exact value of 5? Huh? And you are comfortable. 22/7. That's what you are told. Huh? That is what you are told. Okay? That pi is 22/7. Okay? just for this class, I'll allow you to say that. Not just this class, just for this minute. You'll be allowed to say pi equals to 22/7 and you are comfortable. So in basic math or discrete math, we studied different types of numbers, okay? We started with natural numbers. So what are natural numbers? Numbers like 1, 2, 3, 4, etc., okay? Then all numbers, we start from 0. So natural numbers, we start from 1, 2, 3, 4, etc. All numbers, we start from 0, 1, 2, 3, etc. Then from whole numbers, which set? From whole numbers. Anyone who has done discrete math? Yes. So Irene should be able to tell us. We have natural numbers, whole numbers, followed by integers. So integers are 0 plus or minus 1 plus or minus 2 plus or minus 3 plus or minus 4, etc. These are what we call integers. Then any other set of numbers apart from integers, natural, whole numbers? Rational. So there's what we call rational numbers. So what's the definition of a rational number? What is a rational number? Have you ever seen rationals? Like, example? Huh? Move from away from there. Let's give things which are easier for people to see. Examples of rationals? Huh? Group of 5 is an example of rational, correct. Any other example? How would we find rational? Yes, with like fraction, okay? So a number which can be written in the form A over B, where both A and B are integers, okay? And then we usually say that the denominator should be non-zero. So any number that can be written as a quotient of two integers with the denominator being non-zero, and this can be reduced into lowest form so that GCD of A and B is 1, are called rational numbers. A is an integer, B is also an integer. Now, opposite of rational, irrational, okay? So irrational are those numbers which cannot be written as a quotient of two integers, A over B, such that both A and B solved by the definition of integers. Denominator is non-zero, and we can reduce this to lowest form so that the GCD of the numerator and denominator is 1. Those are what we call irrationals. Do you remember any example for an irrational number? Any example for an irrational number? Yeah. Yes. Root 2, correct? So root 2 is an example for an irrational number. Any other? Any other? Have you done discrete math? For you. Okay. So any other example? Please tell us any other example. An irrational, yes. Yes. Like? Okay, so there are two types of decimals. We have what we call, so we can have a terminating decimal, we can have non-terminating decimal, we can have recurring decimal, we can have non-recurring decimal. Okay, but you can give more other examples here. So for example, root 2, then 3, say root 5, and for those who have done math, this is math. Pi is here. It's an example of an irrational number. And then we have this number here. Whose value is 2 point? Use your calculators. What is the value of E? Is roughly 2 point what? 2 point? Irene? Are you seeing the button with E? Yes. So just in that button, then 1, then equals 7. In that button, in 1, then equals 7. There's a button labeled E. Are you seeing it? Is it on top or under? Depends on the calculator you're using. Top. Then, once you have this, then key in digit 1. Then key in equal sign. What does this mean? Irene. You have to give us the answer. No, we are not taking any answer from any other quarter. There's no question there. Okay, what do you have? 2.7, 1. After 1, 8. Is it 8? Yes, okay, just a minute, so that we are on the same page. 2.7, 1, 8. And then 2, 8, 1, 8, so that number is also an irrational number. So now, if there is no number, what you also have to know, there is no number which is both. No number is both rational and irrational. No number is both rational and irrational. Because if you are saying that this is opposite of this one, then obviously there's nothing in common. Okay? Now, so then now by saying so, then you know that this is a false statement. Because I've said pi is an example of an irrational number. And 22 is an integer. 7 is also an integer. So integer by integer qualifies to be rational. So the correct way of writing this is approximately equals to. So when you put a dot above and below, this approximately equals to, you can use this side. Approximately equals to 22 all over 7. So pi is not equal to 22 all over 7. It's just an approximation of this number. But then for those who are reading things on Google, how many digits does pi have so far? How many digits? This number 5. Actually, they're over 22 trillions. Yeah, so actually, so far, they are over 22.4 trillion digits. Over. So if you have to write the digits which defines pi, and we'll write all these board and not enough, all these walls, even on top, the ceiling and the floor, and we'll not exhaust all of them. Do you have smartphones? Can you Google how many digits are there for pi so far? Can you Google and see how many digits does pi have currently? As of 2024, how many digits does pi have? $62.8 trillion digits. Or as of now, which year was that? Do they provide the year as at 2021? Yes? US? I imagine 105 trillion digits, okay? And that's not the end. So I hope you're saying. Now, the number pi, so what usually just make us to relate between 2 numbers, so it just happen a coincidence that if you take the integer 22 divided by 7, you'll get a decimal which is closer to this number pi. But in terms of the digits which forms pi, they are not exactly the same as what you have here. So imagine, so as of, that was 2024. We have calculated more than 1.5 trillion. I know that there are still people are doing research on those numbers, and they're still computing them. So then now, pi itself, the exact value of pi is pi. The exact value of pi is pi. It's not 20/7. So 20/7 is just another approximation. So demystify this. You are now a very senior math student. That when you see 20/7, don't be cheated that it's exactly the same as pi. It's only that it is a fraction whose digits, when you put in decimals, seems to be closer to a few digits of pi. But the exact value of pi is not 20/7. Because if you make that conclusion that pi is exactly equal to 20/7, then what you mean is that pi is a rational number. Because you see 22 is an integer, 7 is also integer. So know that pi is not exactly equal to 20/7. If it's a math that you have to write this sign, quality sign, put 2 dots, just to be safe. Pi is irrational by definition. So this thing, the few digits of pi, that number itself, that constant pi, is 3.14, and many, many more trillion digits after 4. Now, when you go to fractions, when you say 20/7, then it gives you almost around the same number. So that's why we are doing this course. If we are going to do computations and we have pi, then when you approximate by 20/7, we accept your answer, because we are actually, the exact value of this number is roughly this, but it's not exactly equal to. So we started by saying that the objective of this numerical methods of analysis course is to reduce errors in computations. Now, can you imagine, how would you write 105 trillion digits? Say you want to find area of a circle, pi r squared. And then you want to express this pi in terms of its digits. So far we have 105 trillion. How will you even memorize it? It's very hard. So that's why now we are reducing to this fraction 20/7, so that we can actually do the approximation, because the few digits are congruent or have the almost exact value as the ratio of 20/7. Question? Yes. So yes. It is, how can I explain? The 20/7 is brought into picture because if you are to convert into decimal, then a few of its digits, starting digits, agrees with this constant. But then the way the other values are generated actually is computer programming, which is producing those digits. So it's only that's why we use 20/7 in calculation. We are approximating. But in terms of the classification, pi is pi. This is just used for computation purpose. Okay? So that's what it is. So that's why here we are saying there's no number which is both rational and irrational. So to make things clearer, when you are defining rational and irrational, and you have this thing, it's now, it can cheat you that now you classify this number in this set, which is not true. Because this number already is here. You cannot remember decimals which are terminating and recurring. can be written in the form A over B, where both A and B are integers. So we have terminating, so we can reach a stop, or recurring. You can actually have the same pattern on how decimals are appearing, like say 0.333, then it is B. Then you can always convert these things into the form A over B, where both appear integers. But when we have non-terminating, and non-recurring, which is the same thing that the way pi is behaving. If actually at one fit and take a few digits, fill the first 39 digits or maybe 100 digits, you can actually read them from Google, but do these trillions, you will not be able to read them. So a number like 0.1, 0, 1, 0, 0, 1, 0, 0, 0, 1. Is it terminating? Terminating means as a stop, decimal sum of stop. The answer is no, because you see these 3 decimal points. 3 decimal points mean that this list is continuing indefinitely, okay? And then, is it recurring? Recurring means we have the same interval of repetition. It's not, okay? But we can predict the next number. We can, for this number here, we can predict the next number. Like how many zeros will follow this? 4, then 1. Then next, 5 zeros, it is okay. But then, that's not recurring. Yes, you have just said recurring means there's a definite number of steps which the process repeats itself. Okay? So this number here is also an example of an irrational number. Yeah. So all the non-terminating and non-recurring decimals are also irrational. So the objective of computations, what we do is to approximate. So when we have pi, that is why you will, instead of writing the pi as a symbol when you are computing, you will be allowed to write 22/7. It's not exact value. It just happens to have closer value to the exact value, but the two are not the same. So if you have to write it, it's the best way to put it, not exactly opposed. So significant digits. Significant digits. When you say a digit, that's, or digits, just say digits. Digits used to express a number. Digits used to express a number are called significant digits. Are called significant digits. The digits 1, 2, 3, all the way up to 9. The digits 1, 2, 3, etc. up to 9. The digits 1, 2, 3, all the way to 9 are all significant. Are all significant. Zero is significant when, then you put colons. 0 is significant when. So can you remind me? This is high school work. When is 0 significant? When do you count digit 0 as significant digit? After? 1, 2, 3. For example, if I have 1, 2, 3, 0, is 0 significant? Yes. Okay. 1, 2, 0, 3. Yes or no? Hmm? Can you round off this number to nearest two significant figures? If the instruction in a problem is round off your answer to nearest two significant figures, what would be the answer for this? I remember rules of rounding off are that you don't change the value of the number. Not changing the value of the number means if number is in tens, the number should remain in tens. If it's in hundreds, it should remain in hundreds. If it's in thousands, it should remain in thousands. If it's in tens of thousands, it will remain in tens of thousands. So this is 1,230. So what is this number rounded off to nearest two significant figures? Maybe the only question you can answer in the exam. What's the value? Yeah. 1,001. Correct. 1,001. So then now, can you now tell me? You are the one who gave us this example, and you're the one who is giving us the answer here, and your answer is correct. So then now, so the positioning of 0 in that number, is it significant? Ranges is, so according to what I remember, the instruction was round off to nearest two significant figures. And she has said, from here, we move to this number, which is correct. So in that sense, are we counting zeros as significant, the two last zeros? So they are four significant figures. So your answer is wrong. So if you are counting this as significant, then it means that what you have given us is wrong. But then can you give us the right answer? Yes. Yeah. So remember from 1 to 9, there's no problem. It's always significant, but the 0, that's what we want to interpret. When do you confidently say that this 0 is significant in a number? Irene, when do you say that 0 is significant? If you don't know, then Michelle should be. Michelle, when do we say 0 is significant? Yes. So that you don't have actually to start doubting yourself, like the way we are doubting ourselves here. Like in this other example I've written, is 0 significant? Confidently or silently? That this is 1, 2, 0, 3. Confidently or silently? Huh? This is from 1 to 1. And I know you are 40 now. So if you are 40 now, from 1 on should be easier to say. So you see the way you are doubting yourself, actually you are just normal. You are just normal. So the way you are doubting yourself is the way the number 0 doubts itself when it's in a given number. The digit 0, the way it doubts itself is the way you are doubting yourself. So there are some special cases whereby we'll conspicuously classify 0 as significant. So 1, when 0 is between two non-zero digits in a number. When 0 is between two non-zero digits in a number. Like here, you can give this example, like the number 1204 has 4 significant figures confidently because this 0 is lying between 2 and 3. So that 0 is significant by default. That is case 1. Case 2, 0 lies to the right of a decimal point. 0 lies to the right of a decimal point, and at the same time, to the right of a non-zero digit. 0 lies to the right of a decimal point, and at the same time, to the right of non-zero digit. And at the same time, to the right of a non-zero digit. So let's give examples here. Like here, if I have 0.240, then this 0 is automatically a significant digit because it's a decimal number and it is appearing to the right of a non-zero digit. So this number will have 3 significant digits. But if I have 0.024, then this 0 is not significant because though this is a decimal number, this 0 is coming before any non-zero digit. So these are 2 significant figures. If I have 1.004, how many significant figures are there? 4, 2, 0. Anyone who says different from 2 or 4? No. But someone who says 2 or 4, they are actually they have an idea. But one of them is correct. 4. Why do we count these zeros as different? The first thing is that these are decimal number, okay? And then these zeros are coming after a non-zero digit. So all of them are significant. So these are 4 significant figures. Then 1.0. How many significant figures? Huh? 1.0. I ran 2, 1, 2. Why?
Because
after non-zero digit and decimal number, okay? Or 2. So there's no silence about talking about this zero. It's digital is significant by the position of this number. So 2 significant. Then 1 significant figure. Then 1.003. So I hope you are seeing the difference here. Then when we'll be computing errors, the least unit of measurement in this number is 0.01. So times a half, 0.05. Is different from the least unit of measurement here, which is 1. Then the error will be a half. This number, the least unit of measurement is to 1 decimal point, so it will be 0.1. So error is a half of that, which is 0.05. So you have to be very careful on what you are writing, because 1.0 and 1 may not necessarily be implying the same thing. Because the error in this number and the error in this number, they're not the same, similar to this other number. Then 3 are specifically indicated to be significant. And we are talking about the numbers of zeros are specifically indicated to be significant. Like this number we had 1, 2, 3, 0. Then Grace told us that to 2 decimal to rounded off to 2 significant figures would be 1, 2, 0, 0, which is correct. So with that instruction, then already it disqualifies these 2 zeros from being significant. We only count this. So when we have this number here, these are to 2 significant figures. If you want to say to 3 significant figures, 3 significant figures. With the instruction that round off, for example, you are doing calculation and you have 1200, and the instruction was round off to 3 significant figures. We usually start from the left, okay? Then, if you want to round off to nearly 3 significant figures, then you look in the 4th position from this side. So this being 0 does not change the size of this position. So the position remains the way it is. So I'll have 0, this is 2, this is 1. And we replace this position by 0. So when the instruction is round off to 3 significant figures, then in this number, this 0 here will be significant. But unless that instruction is given clearly, then this remains to be 2 significant things. Okay? Irene, are we together? Good. I knew that we are not together. Can you tell me? I want to draw. Let's draw a small tape and then we discuss. Probably be able to understand something. So number, significant figures, and then number of significant figures. That's 7.89. That's 7.89. So what are the significant figures in this number? Or significant digits in this number? Yeah? Yeah? 4 will be here, number of total there 4. So what are the digits here? 3, 7, 8, and 9. Those are the significant digits. Then 5, 0, 9, 0. What are the significant? Okay, maybe let's start, but let people are familiar with how many there are. So how many are they in this number? How many significant numbers are here? You may be the only serious from your village, serious person from your village. Huh? 4. This 0 is significant. Huh? Is this last 0 significant? Huh? Is this last 0 significant? Don't tell me that what we have discussed, actually, I was the only one discussing. Why were we saying that? We started by saying by default 1, 2, 3 up to 9, they are significant digits. 0 is significant only when. So is this, when I write 5090, is this 0 significant? Huh? So we'll have 5, 0, 9. These are 3 significant figures. 7.00. There are 3. That's what we have. Because this already, there's a decimal point, you can see them. So these 0 are appearing before 9, so they must be significant. So this will be 3, 7, 0, and 0. Then 0.0082. 2. So 282. Then 0.00620. So this 0 is confidently significant, okay? What is a decimal number? These others are not. So this will be 620. These are 3. Then the other number is 5.2 times 10 raised to 4. I hope all of you know what this form is usually called when you write a number in this form. Standard form, okay? Or scientific rotational form. So this is standard form or scientific form. So how many significant figures? How many significant figures are that number? 6. 2. Why 2? Why change the mind? Why have you changed your mind? Because only 2. Confidently. Yeah, because this, when you say 5.2 times 10 power 4, please don't confuse the usual decimal numbers with each other. Because if you are to convert this number, it's 5 2 and then multiply 3 zeros, okay? Which will be a non-decimal number. Then those zeros are, unless we are specified, then just 5 2 significant figures. And then if I have 3.506 times 10. Yeah, 4. Because we just move this decimal here. Count over. These are 4. 3.506. These are 4. Correct. Then 10 times 8 times 10 power minus 3. What will be the next number is 10. 8 times 10 power minus 3. 8 times 10 power minus 3. 1. So you only 8, okay? Right. So that's what we normally have. So we are studying about error analysis. So what is an error? What is an error? What is an error? From your form 3 work? Don't tell me error is a mistake. This is not English class. Don't tell me that error is a mistake. No. That's not the definition that qualifies to be in this class. What's an error? Error? So say error is the difference between the actual value. Error is the difference between the actual value. In brackets, actual can also mean exact or true. So the word actual can also mean exact or true value. And the approximate value. And the approximate value. So actual, true, or exact mean the same thing. So the difference between these two will give us error. And then absolute error is now the absolute value of this difference. Absolute error is given by this. So the difference between true minus true and approximate, then you if the sign is negative, you know that negative sign. Types of errors. Types of errors. Types of errors. Types of errors. So there's what we call inherent errors. Inherent errors. Then for inherent errors, you say these are errors. These are errors involved in the statement. These are errors involved in the statement of a problem. These are errors involved in the statement of a problem. Then full stop. Next, you say on the same. When a problem is first presented, when a problem is first presented to a numerical analyst, when a problem is first presented to a numerical analyst, it may contain certain data or parameters. When a problem is first presented to a numerical analyst or a mathematician, if you like, it may contain certain data or parameters. If the data or the parameters, are determined by physical measurement, if the data or parameters are determined by physical measurement, do you expect them to be exact? Obviously. So you say they will probably differ from the exact values. They will probably differ from the exact values. These errors are examples of what we call inherent errors. Then there's what we call number 2, analytic error. Analytic errors. Then you say, these are the errors. These are the errors involved. Okay, errors introduced. These are errors introduced due to transforming. These are errors introduced due to transforming a physical or mathematical problem. These are errors introduced due to transforming a physical or mathematical problem into a computational problem. Into a computational problem. For example, consider sin x. If you're to write sin x as a series, first term is a series. Yes. If you work out the Maclaurin's expansion of sin x, what do you get? If you are to write it as a series. Hey, how did you survive in MAT325A? That question was not set. Yeah, so sin x is the same as x minus x cubed over 3 factorial, then plus x power 5 over 5 factorial minus x plus 7 factorial plus other several terms. That is sin x, if you are to write it as an infinite series. Then you say, if we compute sin x by using the formula, if we compute sin x by using the formula, sin x So I ignore the other terms and I pick just this first three terms. Then it leads to an error. Then it leads to an error. Then it leads to an error. Similarly, the transformation, of the equation e power x minus x equals to 0 into the equations the transformation of the equation e power x minus x equals to 0, you replace this by this, involves an analytic error. Involves an analytic error. Because you know, e power x by default is given by 1 plus x squared over 2 factorial plus x power 3 over 3 factorial plus x power 4 over 4 factorial plus several other terms. So these are the infinite series for the exponential e power x. So if you decide to now, instead of use the function the way it is e power x, to use a series and you only pick the first 4 terms, represent this one, then it means that from here to infinity, you are assuming those terms. So they will lead to an error. And that transformation is what we call that error which results in the transformation from the given mathematical problem into now the process of computing the value, what we call analytic error. So other errors include, so how do we get the rounding off error? For example, so I just write a hyphen and say, these are errors, these are errors, these are errors which results from, these are errors which results from using fewer digits of a number, using fewer digits of a number, using fewer digits of a number through rounding off, through the rounding off process, through the rounding off process. E.g., instead of using 2.534678, so this is a number we have. If we use 2.3, then the rounding off error is it. Assuming the actual number is 2.34678, then you use 2.3, rounding off this number to nearest one decimal point. So nearest one decimal point. So what will be the value of the round of error? 0.04678. Yeah. So this is what would be the value of the round of error. Then lastly, what we call truncation errors. Truncation errors. Truncation errors. Errors which results from cutting off some digits, or some terms of an infinite series. So, for example, this number e power x is given by 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x power 4 over 4 factorial plus x power 5 factorial plus other several terms. So if we decide to use e power x 1 plus x squared over 2 factorial. So instead of me having all of them, if you are to go to the section, all of them, just approximate this by this first 3 terms. Then it means that I'll have cut this series from that point. So this part that remains is what will constitute my truncation error. So truncation error will be these terms which are actually not included in the process of computing this e power x. So the truncation error will be x power 4 over 4 factorial plus x power 5 over 5 factorial plus all other terms which follows. Next one. Oh yeah, this okay, this is an x power. That is my cutting process. But if I was to remain this and then I pick it from it, okay? And mostly when you are dealing with an infinite series, if you are to compare x power 4 over 4 factorial, assuming x, okay, anyway, x is one value, x power 4 over 4 factorial and x power 5 over 5 factorial. Which one is larger than the other? X power 4 over 4 factorial, x power 5 over 5 factorial. If x, take x to be, say, x is a positive value. If x is positive, then what of the two values, two numbers is larger than the other? X power 5 over 5 factorial or x power 4 over 4 factorial? Is larger than the other, okay? Yeah. So in most cases, when we are dealing with expressions or problems which involve a series or a formula that has many terms, and we want to compute truncation error, and I hope with that in mind, you know that the next terms which follows after this 5 factorial will be much smaller than this. You get the absolute value of each of them, even if these numbers are negative. If you get the absolute values, then the rest of the terms will be still much smaller than this one here. So this will be the most dominant term. So in most cases, to compute the truncation error, because we cannot list all these infinite terms, where's the anti-causation of this one? So we just pick, we assume in this case the truncation error. So epsilon in this course will be the notation we use for error. So epsilon sub t will mean truncation error will be approximately x power 4. So what I'm trying to illustrate is that for an infinite series, to approximate the truncation error, once we have used part of the series, the error is approximately equal to the first term in that remaining part of the series. This is the most dominant term, dominant part. So will be assumed to be this term x power 4. So which means then now, if we are to use these first three terms, then the transition error will be that x power 3 over 3 factorial. So that's what we'll assume to be our transition error. For the time, how many hours did you pay for this course? How many hours did you pay for this course? 3. So how much do I still owe you? 1 hour, 18 minutes. Or you want to donate it? So that's what we'll have. But the remaining detail, not very complicated. I know you. We have met in a different course. I know how. It's always good to know your experience. I know how. Like error propagation. Do you have problems in error propagation? You remember from trivial error propagation? Ranges? You can't remember. Next. Next person is called Anne. Are you Anne? So Anne, do you remember error propagation? Okay. That's why you are paid for this program. Yes. So we have to make maximum use of your money. So okay, I'm not just for 20 minutes, okay? Yeah, only 20. I will not take all day. So error propagation. Error propagation. So what you're going to do is to derive approximate values of errors when you are doing the 4 operations: addition, subtraction, multiplication, and addition. And it's a pretty very easy exercise. So we'll start by saying let x and y be exact quantities. So we use the notation x and y to be exact quantities. Then let by x and by y be approximate quantities for x and y respectively. So when you see about x, you know that that is an approximation value of x. When you see by y, you know that that's an approximation value of y. Okay? Then let epsilon sub x, epsilon sub y be positive error quantities, small positive error quantities in x and y respectively. And thus we'll take that as the convention in our notation, that when you see bars, you know that's approximate value. When you see a letter without a bar, then that's the exact value. When you see epsilon, it's an error, okay? So that's it. Before the derivation, let it be very clear that by definition, we know that by definition, error is always given by exact minus approximate, okay? Yeah. Exact minus approximate. Exact value minus approximate value computes the error. Then number 2, absolute error simply means magnitude of error, which is magnitude of exact minus approximate. That's by definition. The absolute error will mean exact minus approximate. So we'll use RFE to mean relative error. How do we compute relative error? How do we compute relative error? From a Form 3 work. Relative error is given by absolute error over actual value, okay? Yeah, absolute. So the word actual are exactly the same thing. So we are the change. And then which other thing is the mean? Percentage error, okay? Yeah. Percentage error. Is relative error times 100%. So that's what we have. So these are the backbones of things we are going to define error propagation. I have this. Okay. So then now the first operation is addition. Addition. So 1, addition. Addition. So I want you to tell me from what you have said as the basic definitions, you already know from where you're coming from. What is the relationship between x by x, error in x? How are those 3 quantities related? X by x, error in x. Right? I want an equation connecting the 3.
Yes.
Ex equals to? Yes, okay. Because that's what you said as an error. Error is exact minus the approximate. So we have error in x is the same as x minus by x. All that should be obvious from the definitions. Then error in y should be y minus by what? Okay. Yeah. So which means then if I make my x the subject, what do you like it? By x equals to, if error in x is x minus by x. So what is by x? X minus error in x, okay? Yeah, because it's like take this to the left, then this to the right, okay? So x minus error in x. Call it equation 1. Then similarly, by y will be by y, y minus error in 1. Call it 2. So then now, we are in the operation of addition. So let's sum the two questions. So 1 plus 2 gives, so when you are adding two equations, you add left hand side, also add the right hand side. We'll have by x plus by y equals to x minus error in x plus y minus error in 1. Okay? And when you are adding, you can always rearrange the terms. So we can bring the exact quantities together and error terms together. So we can have x plus y minus error in x minus error in 1. Okay? We are not changing the equation, we are just rearranging the terms. And then by x plus by y equals to x plus y. So if I introduce bracket there, what if the sign between error in x and error in 1? Plus, because now the minus will be affected outside, okay? So error in x plus error in 1. That's what you have. Then let's talk this language here. We can say error in x plus error in y is the same as x plus y minus by x plus by y. Are you convinced? If you make this a subject, if you take this to the left, then this is what you have. Right, okay? Now, so these are sum of exact quantities in exact sum, okay? Then sum of approximate sum, okay? So then now, when you say this is it's like if I like this is capital X. So if I call this capital X, you don't know anything. If I decide to call this capital X, what name should I give this? With the convention we are using. Bar capital X. Yeah, because this is involving the variables without a bar. These are parts, okay? So it's like this will be now capital X bar, capital X bar. So it's like now we have capital X minus bar X represents from where we're coming from will be error in X, but now that's capital, okay? But that capital is X plus 1. So we say I is epsilon X plus epsilon Y is the same as epsilon X plus 1. It's like what you have said, all this you call it epsilon capital X, but capital X is X plus 1. So therefore, sum the error in sum is same as sum in error. Only that will make sense. But if I want to get the error, if I know the error magnitude of X and I know error magnitude of Y, then I'm asked to find the error in X plus Y. It's as good as just adding the two errors. And remember, these are absolute, these are positive values. Absolutely. That's the case. Then 2, subtraction. Subtraction of difference. Subtraction, difference. The game is the same. To write these first two lines. Write these first two lines. Write these two lines. Don't just good. So what are we doing? We are subtracting, okay? So let's just say 1 minus 2. So have this minus. Then we have this minus. We are subtracting equation 1, 2. So we'll have x minus y equals to x minus x. So when I open the brackets, I will have minus y minus 1, then plus y. Hope you understand where the plus is coming. Okay? So this is the same as that x minus y, x minus y minus x plus y. Just rearrange the terms. Then we can now introduce brackets to the terms having approximate, terms having exact, and then the error terms. So I can say into brackets by x minus by y, x minus y. So if I factor out minus, what is the sign between error in x and error in y? Negative. So minus. So which you can also in similar manner say error in x minus error in y equals to x minus error in y minus by x minus by y. So by default, the right-hand side defines maybe I'm taking the same conventional notation. Huh? So x minus y defines exact difference, okay? Then by x minus by y, that's approximate difference. So the difference of the two should give us error in x minus y. So you can say error in x minus y is equals to error in x minus error in y. But with this negative sign, with the negative sign, we get the absolute value of each of the two error terms. So which converts this into the same form as saying error in x because this is already positive. These were already assumed to be positive plus error in y. I know what I'm saying doesn't make sense. That one I know. So Irene, let me give the example for us to be the same set. I hope you remember in Form 3, if I give you a measurement like 2.9 centimeters, and I gave you another measurement like 1.3 centimeters, just for example. Okay? Then, what is the error in X? How are you getting errors in computer? You have questions. Do you remember how we used to get the errors? Of what? What is the least unit of measurement in this measurement? 0.1. So then you usually you take a half of the least unit of measurement. So then error here becomes a half of 0.1, which is 0.05 centimeters, plus or minus. Then what will be error in 1? This unit of measurement, we may have 1.3. Is this unit of measurement is determined by, so this decimal, how many, this number is to nearest how many decimal points? This number, 1. So that's why I'm getting 0.1. It's always 10 times raised power negative m, where m is the number of decimal points. Okay? So this is 1 decimal point. That's why they're saying 0. That's why she said 0.1. Then if I have 1.3, the same number to nearest 1 decimal point. So 0.1 still. We divide by a half, you get 0.05. So 0.1/2, 0.05 centimeters. Then we want error in the difference of x minus 1. So this is what you are doing. If you remember, if you can recall what your teachers told you in high school, that error is always average of maximum minus minimum. Do you remember such a thing? Yeah. Regardless of the operation you are doing, you get the maximum value and the minimum value, then divide by 2. So this is the error general formula. Maximum value, whether you are doing addition, so maximum sum, if you are doing subtraction, maximum difference. So then now, so which means then now x lies between, if error is 0.05, so the maximum is 2.95, then the minimum, can you subtract 2.9, 2.85. Then y will be between max the 1.35 and 1.25. Okay. So we have this. If I have my x here, or say I have my y here, I have my x here. Then to the left, I'll have y minimum. To the right, I'll have y maximum. This I'll have y x minimum. This one I'll have x maximum. So by default, what is to the left is minimum, what to the right is the maximum. Okay. So our interest is to get the maximum difference. Will it be x what minus y what? X is this side, y is in this side. So from this number, x minus y will give a bigger gap between which numbers? X minimum or x maximum, y minimum or y minimum. From this number. Maximum minus y minimum. That's what will give the largest possible difference. Yeah, you can see from here. This is actually what is going to be larger line. Okay? So this will be x maximum minus y minimum. Can you give me the answer? X maximum is 2.95 minus y minimum is 1.25. 1. Exactly 7. Then let's get the minimum difference. So x till x minus 1. So remember, we are this side and this other side is what we are getting. So which two values will give us smaller? X min, y max. So x min, y max. So x min is 2.85, y max is 1.35. 1.5. Then now we can use this general error calculation, the max minus min divided by 2. So we'll have error in x minus y will be a half of maximum, which is 1.7 minus minimum 1.5. What do you guys think? 0 point? 0 point. Sure. Okay, I know it's a wrong answer, but good for learning. I know you are tired. It is either if you want to use 0.5 few times, if you want to use the fraction, then times. So 0.1. Okay? So this is the error between error in x minus 1. And then we say the error in x by default was 0.05. Error in 1 was 0.05. If you add the two, what do you get? Error in x plus error in 1. 0.1. So Irene, this is what I was saying. That in this derivation here, negative sign came in because of the computation. But in terms of the magnitude, that's what I'm saying. Error in x minus 1, you this negative, because we are only having error values, we are getting that. That is why this minus is changing to plus. So absolute here. So then it turns out to have the same exact structure. Yeah. If you maintain the negative, then it will be to assume that if you are told to find the error in x minus 1, for example, if x given by 2.9 is y given, error is 0, which is not true. Okay? Yeah, that's what I was saying. Should we stop there?
Yes.
We should. So let's stop there. We'll pick from error in multiplication and division next time. Okay? Yeah.